Hey, Dr. J. Today we're going to learn about Riemann sums, named after the 19th century European mathematician George Riemann, who lived to the ripe old age of 40 between 1826 and 1866 in what's now Germany. There's a long history behind his very short life and how he died of tuberculosis. I'm not going to give you a history lesson today, but I do think it's interesting when we learn a new recipe, formula, technique, and it's named after a famous mathematician to at least have their name. It's George, and I did not misspell that. That's the spelling of the day. His entire name is George Frederick Bernard Riemann. I'll spare you all the details. And the goal, what his name became famous for, among other things, is to find the area under a curve. And I will mention, when I say under a curve, we mean between the curve and the x-axis. So throughout this lecture, when I say under, I mean between the curve and the x-axis. So if I have a curve, here's my x-axis. This is what we mean by the area between the curve and the x-axis. And we usually do it on an interval. Or you could say between. I usually say on AB, which really just means between x equals A and x equals B. So there's A, there's B, and we want to know this area between the curve and the x-axis and on the interval AB, again, between A and B. So this is what we're looking for. How do you find that area? Now, the graph I just drew looks sort of circular in nature. It's not a circle. We won't be doing circles in this lesson. But we will be doing classic functions that appear in algebra and in calculus. So let's get right into it with example 1. This is just sort of setting up what our goal is to be able to find that area. And so what makes a Riemann sum? I don't know why I just erased that. A Riemann sum is the sum of at least two rectangles to approximate the area. So underneath this graph, we will draw at least two rectangles, and then we will add them up. I should say the sum of the areas. Because we have to have the area. So we're going to say, well, why don't we just take a rectangle and put rectangles underneath the function and add up these areas and say, well, the area under the curve is approximately the sum of these two areas. We'll say A1 and A2. And so that is one way of achieving our goal. So I would say the area is approximately A1 plus A2. All right, that's the general idea of what we're going to be doing today. Let's get right into it with an actual function. The one I just drew is very close to what we're going to do. But let's be a little bit more specific about it now that you see the goal. And then when I use these terminologies like the Riemann sum, what I actually mean is to add the areas of two rectangles. All right. So, example 1. Prologue is ended now. So consider the function, let's do a classic parabola. 3 plus 8x minus x squared between, let's go x equals 0 and x equals 4. Now, I'm not going to spend a whole lot of time drawing the graph. I'm going to do a classic calculus graph, which is, let's plug in 0. So we'll go from 0. We'll call this 1, 2, 3, 4. So the graph essentially looks like this. It crosses the y-axis at 3. The y-axis is not going to be to scale. It's just going to look like this. Very similar to what we just had. So you see how nice that was? I'm only going from 0 to 4, so I don't really care too much about this. I only care about 0 to 4. Okay. So there are two methods. There's the left endpoint approximation. That's method number 1. And method number 2, the right endpoint approximation. So we have two different methods that we will explore, at least in this example. Turns out there's a lot more than two methods, but we will talk about these two methods. And while I have the graph here, without screwing up the graph too much, let me explain the difference, right? So we're going between 0 and 4. Let's just start with two rectangles. We call those subintervals. Subintervals. The symbol we use for a subinterval is n. It's the number of rectangles. Okay, let's start with the left endpoint approximation. I'll do the entire problem with left endpoints, and then we'll do the whole thing again with right endpoints. All right, this is example 1 is going to be a deep one, but it's going to only have two rectangles. So we divide the interval into two pieces. All right, like this. And then we have to decide where to put the roof. That's what I call it. The top of the rectangle. So if we use the left endpoint, for each rectangle, you choose the left endpoint to be the roof. Notice you're missing a whole lot of area here because you've chosen the left endpoint, which is why we'll have two methods you'll see in a minute. And then for the second rectangle, we choose the left endpoint of the second rectangle. And then we can clip the rest of this function. We don't need it. We're only interested in the interval from 0 to 4. So this is our left approximation. We'll call this A1 and A2. So the left endpoint approximation. A1 plus A2, which is equal to. Now, I'm going to make this a lot more complicated than it needs to be because I want to get some very important formulas down. In this diagram, it is so obvious that this is 0, this is 2, and this is 4 because the interval was nice even numbers from 0 to 4. We were cutting it in half with two rectangles, and so clearly the middle here is 2, right? However, with the left endpoint approximation method, we need to have some kind of a recipe for the width of each rectangle. And so the symbol for width is delta x. That's the width. So that is the width of the first rectangle here. Delta x1 is the width of the first rectangle. All right. Times f of A. A is the left endpoint, which is 0. So this is A. So that is your A1. Let me spread this out a little bit. So all of that is A1. Plus A2. Well, that's the reason why we have this recipe, because now you can just go to copy it for the next rectangle. Delta x2, the width of the second rectangle. All right. Which you know is going to be 2, right? Clearly the width of that rectangle is 2. I will mention that if they are the same, you could just say the width of each rectangle is the same. So we don't really need the subscripts anymore. I could just say delta x. I mean, sure, this is delta x1 and this is delta x2, but because the width of each rectangle is the same, we may omit the subscripts. Okay. And then f of A plus delta x. Now that is a very complicated mathematical calculus way to say the width of this first rectangle times the height plus the width of the second rectangle times the height. So let's figure out who everybody is now. All right, let's do some scratch work. Delta x. Delta x is clearly equal to 2. Clearly, right? However, there is a formula. If you can't see it, if you can't see that the delta x is clearly 2, in this example, you could just count, right? The width of this rectangle is 2. The width of this one is also 2. There's a very easy formula. Delta x is always b minus a divided by n. All right, so here's my b, 4, minus, so b is 4, minus a, 0, divided by n, which was 2. So that's 4 divided by 2, which is 2. So I'm going to keep this formula around because we will need it in many of the examples after example 1 where you can't just see how wide each rectangle is like you can in this example. So you do have to have the formula as a backup. All right. So let's continue our calculation. Delta x is 2. times f of a, so that's f of 0, plus delta x again, which is 2, times f of 0 plus delta x, which is 0 plus 2. So our approximation is 2 times, now f of 0 you can clearly see, right? F of 0 is 3. If you can't clearly see that, go back up here and plug in 0. And you'll go, oh yeah, I see how you got that now. That's the easy one. This one, f of 2, 0 plus 2 is just 2. I mean, it's not going to be hard, but it's not going to be as easy as that one. So f of 2 is this point right here. Right, how high is this point? F of 2 is 3 plus 8 minus, 8 times 2, sorry, minus 2 squared, which is 3 plus 16 minus 4, which is 15. So 2 times 3 plus 2 times 15. I probably could have started the problem here if you can see very clearly the width and the height of each rectangle. Let's just double check that before I calculate it. The width of the first rectangle is clearly 2, and its height is 3, right? So width times height. Or sometimes we say width times length, or sometimes we say base times height. There's a lot of different ways to say it. It's just multiplying the two sides of the rectangle. So that's clearly 6. That's the area of the first rectangle. Let's just double check the second rectangle. The width of this rectangle is also 2. Yeah, from 2 to 4, the width is 2. So delta x's are both 2. And the height of this rectangle is 15. If I would have been more precise at the beginning, when I drew my original graph, I would have saw that that was 15. But it's okay. You don't need it until you need it. And so our first approximation is 6 plus 30. So we would say the area is approximately 36 by left-hand approximation. LHA, left-hand approximation. All right. So, not a very good approximation because notice it leaves out this big chunk right here. Right? I don't know. If you see where I'm going with this, I'm doing this example mainly to show you the technique and the notation and the recipes that we're going to use, but clearly we're going to have to use more than 2 rectangles. In fact, this will be the only example in which I only use 2 rectangles. It's the bare minimum. It's the laziest approximation. Not very good, but it'll work. All right. So now we'll do right-hand approximation. So let's redraw our graph. I go all the way to 4. I erased that temporarily because I didn't need it, but now I need it. All right, so now the right-hand approximation. So this is going to be the height of the second rectangle. And then this will be the height of the first rectangle. And you'll see clearly that the first example, the first attempt, the LHA, was an underestimate right? Under approximating. In my second one, the right-hand approximation is going to be an overestimate because the rectangles are going to go above the curve. Okay. So let's do the same calculation here. Where's my pen? There's my pen. So right-hand approximation, A1 plus A2. A1 is delta X times, now this time we're not using 0, because that was the left-hand one. This time we're using 2. So we go F of A plus delta X. So we're going A is 0, plus delta X to get to our right-hand point. A plus delta X. Plus delta X times F of the last endpoint, which is B. So again, delta X is 2. A is still 0. Delta X is still 2. And then F of B is now F of 4 to get this right-hand point, which is like the roof of the rectangle. And my drawing is not to scale. We know this one. That's the nice thing about doing both of these is if you've already done F of 2 and you know it's 15, you don't have to do it again. That's going to be 2 times 15. The one we don't know is this one, F of 4. And in my picture, it looks like it's just a little above 15, but I wouldn't trust the picture. I would use the formula to figure out what F of 4 is. So that'll be 3 plus 8 times 4. I'm using this function, minus 4 squared. 3 plus 32 minus 16. So that's 19. F of 4 is 19, right? Oh, I guess it is just a little bit above it. My drawing was better than I thought it was. Double check that. 32 minus 16 is 16 plus 3. Yep, 19. Good. I was criticizing my graph because I didn't think it was that close to reality, but not bad for just freehanding it. And so then we have 2 times 15, 2 times 19. So 30 plus, what's that, 38? 2 times 19, 38. So our right-hand approximation is 68. I usually use equal signs while I'm calculating, because, I mean, these are all equal to, but these are equal to the rectangles, but then the rectangles are approximately the area under the curve. So I switched to an approximately symbol at the end. And so this is by a right-hand approximation. So there you go. That is the simplest example of a Riemann sum with 2 rectangles, calculating left-hand versus right-hand approximations. Clearly, we need more rectangles. To get a better approximation, we need more rectangles. Let's just slowly turn up the number of rectangles by going to 3, I guess, seeing if that does any better. So consider f of x equals 9 minus x squared. Oh, no, not that one. That's the wrong one. 8 minus 1/2 x squared on the interval or between, whichever way you want to say it, -1 and 2. Now to speed things up a little bit, I have a graph pre-prepared for you. So ready? Wait for it. Ta-da! All right, it's already been graphed. So this is my function. I guess f, or I could just say y, same thing. So this is roughly the graph of 8 minus 1/2 x squared. So this is 8. The y-intercept here is 8. There's an x-intercept down here at 4. There's another one off the screen over here at -4. I could get out of the way of myself there. We don't need it anyway because we're only going to -1. So we're going to go from -1 to 2. And let's just do left hand. By left hand approximation with 3 rectangles. All right, so we've got delta x. Let's do that first. Practice the recipe. B minus A over N. So B is 2 minus A. A is -1. Be careful with double negatives. I've seen people go 2 minus 1 and get it wrong. It's 2 minus -1 divided by N. N is the number of rectangles, which is 3. So each rectangle will have width 1, which I hope is pretty obvious when you see the graph. There's your first rectangle at -1. And then my second rectangle will be right here. Yeah. And then my third rectangle will be right here. And you'll notice as you're doing this, some of the rectangles will go above the curve, like this one and this one, and some of the rectangles will end up underneath the curve. The key is to be consistent, so because we're doing left-hand approximations, I can't do, at least not yet anyway, maybe someday you can, but the way that I'm presenting this, you have to choose either left or right, so you either choose or you just do what I've chosen for you. I've chosen for you left, so you always have to use the left-hand point on each rectangle. All right. So what do we got? We got a A1, A2, and A3. We're going to add up the areas of 3 rectangles. This took up a lot of space, so why don't I just copy the result here? Delta x is equal to 1. I think you probably could have seen that in the graph. For a lot of the introductory examples, you can see it in the graph. I'm just going to put this off to the side here. So I've got A1 plus A2 plus A3. And I'm using left-hand endpoints. So that's going to be delta x times f of A, which is -1, plus delta x times f of A plus delta x. Plus delta x times f of A plus, I'm running out of room, 2 delta x. Sorry about that. Maybe I'll rewrite that in a second. So delta x is 1. All of these delta x's are going to be 1. F of A, remember A is your left interval endpoint, so that's -1, plus another delta x times f of a is again -1 plus delta x, -1 plus 1, plus 1 times f of a plus 2 delta x. So let me just blow that up right here. That says a plus 2 times delta x. You see, because we're moving over 2 rectangles to get to the next endpoint. So we're starting at A, and we're moving over to the third rectangle. Now, all of this mathematically looks very complicated, but you can get all of that information by looking at the graph. However, there's going to come a time, in just a few minutes, where you might not see the graph so easily, and then you'll have the recipe to guide you. All right, so we're going to need the function. So we got f of -1. I'm just omitting the 1 times because that doesn't matter in this case. That's one of the advantages of having the delta x be 1. It means when you're adding these up, you just add up the function values. This will be f of 0, which that's the only point we actually know, which is 8. And then this will be f of -1 plus 2, which will be 1, f of 1. So I need to know 2 more points on my graph. Let's just confirm that we have the f of 0. F of 0 is the easy one. Yeah, that was the easy one. That was the one you could see right from the graph. It's clearly starting up here at 8. Let's do f of -1 and f of +1. And you can actually kind of see by the graph that they will be the same. So I've got 8 minus 1/2 times -1 squared. 8 minus 1/2, so 7.5. And notice that 8 minus 1/2 times +1 squared is still 8 minus 1/2, which is still 7.5. I hope that's obvious from the graph. It might not have been obvious if you couldn't see the graph. I don't know. All right, so then we got f of -1 is 7.5. F of 0 is 8. F of 1 is, again, 7.5. So our area is 15 plus 8, 23. And again, I usually use equal signs when I'm calculating, but for my final answer, I would say A1 plus A2 plus A3 is equal to 23. Therefore, the left-hand approximation is approximately 23. Just to be, extra annoying. Yeah. Don't worry, I'm not going to fool you into which symbol to use. It'll be clear by the question whether I'm asking for an approximation, which I am, because that's all we know how to do so far. I already tossed the graph off to the side, but the area under the curve, this one's actually a little bit better, is pretty close to 23 if we were to calculate the exact area, which is the ultimate goal of Chapter 4. But we're not quite there yet. Piece by piece. Well, let's do 4. So approximate the area under y equals 1.5 times the square root of x between or from, different way to say it, x equals 4 to x equals 8. Again, let's use left hand approximation with 4 subdivisions. That's width. And this is the last one that I have pre-prepared for you, and then you'll have to gruelingly watch me graph some of these. So here we have the function y equals, or f of x equals 1.5 times the square root of x. It's really nice. So this is A, this is B. It's really nice when you get delta x is equal to 1. This is n. So your delta x is 8 minus 4 over 4, which is 1. That's nice when that happens. You can also see it in the graph here. If I start at 4, I will get, there's my first rectangle. Remember, I always have to use the left-hand point. Then I go to 5. Then I go to 6. And then 7. Now, even though the rectangle goes all the way to 8, because I'm doing left-hand approximations, I'm going to use 4, 5, 6, and 7 for my rectangles. So I've got A1 plus A2 plus A3 plus A4. I'm getting pretty good at this now. The delta x's are always 1. I'm going to write them down anyway, though. So delta x f of 4 plus delta x f of 5, etc., etc. Delta x f of 6, delta x f of 7. The delta x's are all 1. I don't even know why I'm writing them, because they're all 1. I would write them just so that you know they're there, because they won't always be 1. In fact, looking ahead, this is the last one where they're 1. So it's not realistic, but it's nice when it happens. But I mean, it really limits how many rectangles you can have, right? I mean, basically says, on this interval, if you want them all to be 1, then 4 is the most number of rectangles you can use, which is fine, but we're eventually going to use a lot more than 4. I mean, we might get up to 10 or 12 rectangles at some point. I don't know. We'll see how much time we have today. All right, so unfortunately, this graph has a square root, so I'm going to need my calculator to calculate all of these. Oh, by the way, f of x is the same as y, so sometimes it's nice to rewrite functions in function form. And then we'll do some scratch work. So we got f of 4, 1.5 times the square root of 4, 1.5 times 2. That's easy, that's 3. F of 5, 1.5 times the square root of 5. Now this gets kind of messy because now you've got approximations within approximations, but we can handle that. Square root of 5 is about 2.23 times 1.5 So that's about 3.3541. I'm not going to round until the very end, so it's probably not a bad idea to wait to round. I forgot to tell you the directions. We will round to the nearest tenth. But let's wait. Don't round now, because if you round it now to the nearest tenth, by the time you get done with all of these, you got 4 different rectangles, it'll be off by a little bit. So just wait till the very end. So f of 6, 1.5 times the square root of 6. Square root of 6 is about 2.449, and then times 1.5. So that's about 3.6742. And then finally, f of 7. Square root of 7 is about 2.64 times 1.5. And I get, I'm just going to jump right to it for this one, 3.9686. All right, so I've got them now. F of 4 is 3. F of 5 is 3.3541, blah, 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 blah. If you have to, you can keep all of them in your calculator. 4 decimals is plenty. F of 6 is 3.6742. And then F of 6 is 3.6742. Almost got those backwards. F of 7 is 3.9686. So that's probably good enough. So we'll take this one. It doesn't matter the order. Plus, they're all adding 3.6742 plus 3.3541, and then plus 3. 13.996, which is 14.0. Yeah. That's that double 9 rule. So this 9 rounds that 9 to a 10. And then that rounds the 3 to a 4. And so it's 14.0. Because it said 10th, it's not a bad idea to put the 0.0. Although 14 is also correct. But this double 9 thing happens so infrequently, you never know when it's going to happen. But when it does, I just do whatever it tells me to do. I don't argue with the facts. Okay. Not too shabby, huh? And you can kind of see the idea now as we're going along. The more rectangles we use, look at how close this is to the actual area, right? We're only missing these little areas right here, right? So it's pretty close. If I were to use, 8 rectangles or 12 rectangles, you can get very, very precise with these approximations. And then for a little historical reference, George Riemann, he lived in the 1800s, right? He didn't even have a calculator. So you can really appreciate the time and energy that went into doing this longhand, right? If you really want to experience, the world of mathematics, I mean, even just prior to the mid-20th century, having to do a lot of these, we have a lot of advantages now. This problem, was sped up by technology. We also have graphing programs that instantly graph the curve for you and such. All right, well, I don't know. Should we do another one? How about 6 rectangles? I don't feel like doing 5. I don't know why I'm skipping 5, but let's go to 6. Now this one I don't have pre-prepared. I do want to switch to right-hand endpoints. So find the area or approximate the area under the curve f of x equals 6 minus 1/3 x squared. Very similar to one of the ones we did earlier. Between zero and 4, using 6 rectangles. Sometimes I like to write the word 6, just to make sure you're still reading. All right, so between 0 and 4. By a right-hand approximation. Or sometimes we say right endpoints. It's a quick way to say that. Right-hand rule, or RHA, right-hand approximation. Okay, so we have no graph. Yeah. If you really want to see a graph, it looks very much like this. It's very much like this. In fact, it's the same family of functions. This one would be like one, two, three, four, five, 6. Be a little bit less steep, kind of like that. Yeah, we're going from 0. So it's not a bad idea to get an idea of what it looks like. So we got 0, 1, 2, 3, 4. That's my x-axis. 1, 2, 3, 4. Oops. It's a good idea to make sure that it's right. So there we go. Something like that. All right. But now we're doing 6 rectangles. So delta x is 4 minus 0 over 6. Yeah. I mean, it's not that bad, but it's not 1. It's not 2. I mean, the best thing would be 1 or 2, or, I mean, even a half would be better than that. But, you know, it is what it is. So, I mean, you just take it. I probably won't care too much about the drawing all that much, but I'm using right-hand rectangles. So I've got, here's just sort of a rough sketch. I'm using the right endpoint. And I'm just going to very roughly put 6 rectangles in here. 4. Mainly, the diagram is meant to identify the endpoints. That's what the graph helps with. It doesn't have to be perfect. All right, it's just a sketch. But the key is when you read it so that you know what endpoints am I using, because if you plug in the wrong points, obviously your approximation is going to be off. So right endpoints, here is where the roofs, I always like to ask my students, do you say roof or roof? The roofs lie. This one's a little trickier. This one's a little bit trickier, mainly because we have so many rectangles. We got 6 rectangles. I'm going to keep this off screen and I'll pull it back in if I need it to find the endpoints. And I'm also going to work vertically. When you have this many rectangles, you got to find some space-saving techniques to, not take up so much of the space on the board. All right, all the delta x's are going to be the same, so they're all going to be 2/3. right? I'll write that a bunch of times. Yeah, 2/3, 2/3, 2/3, 2/3, 2/3, 2/3 times. Now here's where you have to think. The right endpoint. Right? So that's where the diagram comes in handy. Right. The right endpoint is A plus 2/3, right? So that'll be 2/3, f of 2/3. The next one will be A plus 2 2/3. So that's 4/3, right? You have 2 2/3. Each one of these is 2/3. So you've got 2/3, and then the next one would be 4/3. Yeah. I'm just doing the endpoint, like where the endpoint lies. The next one would be 6/3. 6/3 is just 2. So the next one's just at 2. Yeah. And then the next one would be 8/3. That would be this one, 8/3. That's the next line. And then the next one would be 10/3. And the last one would be 12/3. But 12/3 is just 4. And that's how you can use the diagram to help you find the endpoints of each rectangle, in this case on the right-hand side. I'm doing this intentionally because I want you to notice some patterns. As we increase the number of rectangles, identifying little patterns that help you get to the next point is very easy. I mean, it's not easy, but it's very helpful to make the problem easier. It's a lighter, gentler way to say it. In general, the ith endpoint is f of a plus I times delta x. So it's a was 0. Delta x was 2/3. I usually multiply those so that you can see. All right, let's do A3, right? So there's I. I means index. Does not mean imaginary number. We don't use imaginary numbers in this course. You might have learned them in algebra, but we use the same letter, symbol, but I. So that means if I wanted to do A3, for example, I would say 0 plus 3, so I would be 3 times 2/3, which is 0 plus 2, which is how I got 2. All right, I'm just sort of showing you the general pattern in terms of which endpoint we're talking about. I hope that's not more confusing. Let me maybe try one more here. Because as we get more and more rectangles, it's going to be very important to know how to just pick out a particular rectangle and go directly to that point. So let's do A5, suppose. I mean, I could just look very carefully at the graph, right? So A5 would be right about here somewhere, right? But, you know, suppose my writing is too sloppy and or suppose you don't have a very good graph and it's very difficult to find this point right here, right? Now, remember, once you have this point, it's going to go up here and become the roof of the rectangle. So you got to find where it is on the x-axis first, and then we're going to use the function to find the y value. All right, so let's do I equals 5. that would be this one right here. I said it was 10/3, right? Maybe you believe me. I don't know. I don't know what you see. Does that look like 10/3 to you? It's between 3 and 4, right? It might look like 10/3 to you. You might just be watching the video going, Dr. Jordan, it definitely looks like 10/3. But I don't know. All I want to do is show you how I got 10/3 right here. So you're going to say f of a plus I times delta x equals f of 0 plus 5, because I is 5. Delta x is 2/3. F of 0 plus 10/3. Remember, 5 is just 5 over 1. Yeah, 5 times 2, 10/3. So there you go. F of 10/3. Check. All right. It's a good idea to check that the numbers you're plugging in are the right numbers. Because by the time you plug them into this function, which I'm going to do next, if they were wrong, you'll have to do the whole darn thing over again. Okay, so we're ready for our y values. Yeah, so these are the y values. So it's always delta x times the y value. That's going to be your general formula for area, for whichever one you're talking about. We're going to do all of them. All right, we're going to need some scratch work here. I'll just do some scratch here. So f of 2/3. So I've got 6 minus 1/3 times 2/3 squared. 6 minus 1/3 times 4/9. 6 minus 4/27. I like to simplify this. So 6 times 27 minus 4 over 27. 158/27. All right. Let's do the next one. 6 minus 1/3 times 4/3 squared. 6 minus 16/27. 6 times 27 minus 16. 6 times 27 minus 16. 146/27. And keep going. Now you see why I stacked them. I'm actually going to be looking for a pattern. Let's see if we can see a pattern. 6 minus 1/3 times 2 squared. 6 minus 1/3 times 4. 6 minus 4/3. 3 times 6 is 18. 18 minus 4 is 14/3. 14 times 9. 126/27. 14 times 9. Yeah, 126/27. Which is the same as 14/3. All right, let's see. Next one, 8/3. I'm just going to try to reuse this one. That'll be 64/27. So 6 times 27 is 162 minus 64 is 98/27. You see a pattern yet? Let's see if we can find a pattern. From 58 to 46, it's going down 12. The numerator is going down by 12. Then it went down by 20. Then it went down by 28. Eight. Let's take a guess. I mean, this is where the calculus really becomes, it becomes an exploration in recognizing some things that you might just calculate without looking. I'm going to guess that it's going to go down by 36. So that means I'm going to guess the next one. This is just a guess. That the next numerator, I'm just looking at the numerators because I noticed the denominator is always 27. So I'm just going to guess that the next number is 36 less. I'm going to guess that it's 62 27ths. Let's see if I'm right. Use the function to see if you're right. Plug in 10 thirds squared. You're plugging it in for x. That's going to be 100 27ths. Yeah, 10 squared is 100. 3 squared is 9. 9 times 3 is 27. 100 times 1 is still 100. So I've got 27 times 6 minus 100. What do you know? 62. So then I'm going to do the last one by saying, well, it's got to be the same pattern. This one went down by 12, the numerator. The next numerator went down by 20, then it down by 28, then down by 36. So another 8 more would be down by 44. 62 minus 44. 44? Yeah. Yeah. Minus 44. I'm going down by 44, so that'll be 18 27ths. Whew, this is quite a problem, isn't it? This is quite a problem. Now, you didn't have to do any guessing. You could have just relied on your calculator the whole time. That's fine. I just want to show you, what's coming. All right, so we're ready to add all these things up. So our area, let's simplify all of these. I don't need all of this stuff anymore. That was just my guessing and checking. So I've got 6 areas to add up. The easier you make these numbers look, the easier they're going to be to add when you get to the end. So let's do, yeah, it's not going to be nice. So we've got the area is approximately 2/3 times. Notice these all have 2/3 in them. So I can just put the 2/3 out in front. And then I'm going to add up. And notice they all have the same denominator. They all have a denominator of 27. So I really just need to add the numerators, 158. So if you're getting out your calculator now, just add the numerators, 126, 98, 62, and 18. And there you go. which I could have done this a long time ago, but I wanted to make sure that all these numbers were right. I wanted to demonstrate where they came from. And now I'm waiting to add them all up. So 158 plus, or I'm no longer waiting, I'm adding them up, plus 146. This is where the sum in the Riemann sum really comes in. Plus 126, plus 98, plus 62, plus 18. I'm just going to put equal to for now. 2/3 times 608 over 27. So 608 times 2 is 1216. And 3 times 27 is 81. And I'm going to get approximately 15 point, round to the nearest hundredth, 0.1. And there you go. That's the area. Whew, that was gnarly, huh? Now, I'll tell you why I did this so long. I wanted to show you lots of different techniques. I wanted to show you the stacking method. When you have more than, say, 3 or 4 rectangles and you start to write them side by side, it gets really messy. So stacking them up, number 1 rule. Noticing that the delta x's, the width was the same. And that's the reason why I put the width out in front. Noticing the denominators were all the same. So I was able to write the denominator only once. Noticing a pattern in the numerators, right? So that you were seeing that they were decreasing by a particular quantity. There was a pattern to that quantity, right? And then finally, only having to bust out my calculator pretty much once, right? Now, sure, I could have been using my calculator at every single step of the way, but my answer might have been off by a little bit. I might have got 15.02 or 15.03 or maybe even 14.99 or something. So when you have this many rectangles, it's very easy for the final answer to be off based on early sloppiness, right? And early mistakes, or even just early calculating, using the calculator too soon in the problem. So, I mean, this was quite a problem, but we're done. All right. Wow. I think we only have time for one more. So, example 5. So f of x is negative x cubed plus 16x. Approximate the area under the curve between, I like to say from, it's the same thing. Just it takes up less space, from x equals 2 to x equals 4. Using right endpoints and 8 subdivisions. All right. No graph. Let's try to do the whole thing without a graph. If you're curious what the graph looks like, it kind of looks like this. It's a sort of S-shaped, or sometimes I call it a sleepy or lazy S. It's like an S kind of fell over, right? And we want to know from here to here, and we're going to draw 8 rectangles. I don't even know if I could draw 8 rectangles. That's terrible, but whatever. 6, 7, 8. Yeah, there we go. Close enough. So you see why I'm not drawing the graph. As the number of rectangles increases, drawing the graph becomes very, very difficult. Not impossible. You know, this is an online course. Feel free to take these functions and put them into an online graphing calculator. Desmos is a very good one. A Desmos online calculator. Yeah, if you're curious of what it looks like. Yeah. You could also zoom in on some of these points and find the endpoints and things like that. I don't know if it's going to be any quicker to do that. There's a little bit of a learning curve there, pun intended. But just generally speaking, at this level of calculus, you should look at a function and have a rough idea of what it looks like. You should know where you're starting from and where you're ending. That's about it. The key is using the formulas to set everything up appropriately. So let me just get rid of the graph here. Start with delta x. That's the thing that's going to be the same in all of these. 4 minus 2 over 8. So 1/4. So each rectangle has a width of 1/4. We're doing right endpoints. Yeah, so we have A1 is 1/4 times f of 1/4, right? Or you could write it all out. Sorry, it's A plus delta x. Let me just write it here. I'm going to write the 1 recipe. So that's A1. Maybe I'll write all of them. That's A1. A2, delta x. Sometimes I think it's obvious, but it's not. 2 delta x. Right? That's that index. Yeah, this is what I was calling I. Yeah, the index. It's neat that once you see the pattern, because the only thing that changes in these formulas is that index. Right? And we're going to go all the way, etc., 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 until we get to the 8th one. And we're going to add them all up. All right, they all have the same delta x. That's 1/4. A is 2. So it's not f of 1/4, it's f of 2 plus 1/4. If you prefer decimals, you could do 0.25 and f of 2.25. I avoided decimals last time because they were non-terminating, non-repeating decimals. I guess I've already pulled out the decimals, so I might as well keep them. The next one would be 2 times 1/4, which is 1/2. Right. And you'll notice a pattern will start to emerge. It'll speed things up quite a bit. 3 times 1/4. Right? Remember, all of these delta x's are 1/4. So that's going to be 0.75. And the pattern starts to emerge so that you can just fill them all out. What's A4? Just keep going. 0.25 times f of 3. Yeah, just add another quarter. What's A5? 0.25 times f of 3.25. What's A6? 0.25 times f of 3.5. What's A7? 0.25 times f of 3.75. And finally, A8, if I could squeeze it. Where am I going to fit A8? Here. Sorry, it goes 5, 6, 7, and then 8 is here. 0.25 times f of 4. And there you go. All right, now don't forget that we do have this function up here. This is our function. So we get a little bit of work to do here. So what's f of 2.25? I'm going to do this one with decimals instead of fractions. So 2.25 cubed negative, so it's negative 11.390625. This is what I was trying to avoid in the last one. Just want to show you the two methods, decimals versus fractions. And then 16 times 2.25 is 36. It's a little harder to recognize the pattern, but you might see a pattern. And these are not approximations yet. So I'm writing down all the decimals. This does not go on forever. It's a finite terminating decimal. So. F of 2.5. 2.5 cubed. 15.625. Negative. Sorry, it's negative. Plus 16 times 2.5 is 40. So that's 24.375. 2.75. As soon as you see a pattern, I mean, if you see a pattern, it's much easier to recognize patterns, at least in my mind, with fractions than it is with decimals. 2.75 cubed, negative. So that's negative 20.796875. 2.75 times 16, 44. I'm seeing a little bit of a pattern here. Yeah, 36, 40, 44. Minus 20.796875. 23.203125, etc., 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 etc. F of 3 will be pretty easy. That'll be negative 27 plus 48. You see the pattern? There's a little bit of a pattern here. Look, 36, 40, 44, 48. Oh, the decimals, I don't really see much of a pattern. Negative 27. Yeah, I don't see much of a pattern here. Negative 27 plus 48. My brain is getting tired. You guys screaming at me. It's 11. It's 11. 48 minus 27. It's not 11. It's 21. My brain is losing it. 21. I was thinking 37 and 48. So we're halfway there. 3.25. Are we there yet? Are we there yet? We're halfway there. 3.25 cubed negative. Just think about Riemann or anybody else that did this until calculators became commonplace. Back in my day, you know, you can see that pattern. It's 36, 40, 44. It's this 16x pattern here. Yeah. So at least something is coming out very quickly. 34.328125. 17.671875. It's definitely getting smaller. When we get to the business applications at the end of this course, we return to our business math. We've sort of taken a detour away from business calculus and just into the deep end of calculus. These will be dollars, you know, or perhaps quantities of units. So it might be a little bit more interesting. 13.125. I'm starting to speed up. You'll start to gain momentum as you go along. And remember, these are just the F's. I'm going to have to multiply all of these by 0.25, but I'll show you the trick, which I've already kind of shown you. 3.75 cubed negative. So that'll be negative 52.734375 plus 60. Yeah, see the pattern? 36, 40, 44, 48, 52, 56. Next one's 60. See how it starts to pick up momentum? If this were money, you'd be going, wait a minute, it's going down. That might be good, though. You know, what if this represents cost? That means the costs are decreasing. Yeah, or does this represent revenue? That would not be so good. The revenue is going down. So again, and then the last one is 4. So we don't need a calculator for that. 4 cubed is 64. So that'll be negative 64 plus, 64. Boom, it ends at 0. All right, 4 times 16 is the same as 4 cubed. So those cancel out. It's that curve that I showed you where it just kind of hits the ground at the end. All right, so here's the deal. All of these are multiplied by 0.25, right? I was saving that till the very end. So you can wait, yeah, because those are all the same, you can add all of these together first. Then multiply by 0.25. Yeah. Or you could divide by 4, the same thing. So to wrap this up, just go down the list and add them all up. I still have this last non-zero one. You don't really need to add nothing. So we could start here, and I'm just going to add them up all the way up. Okay, so we got that one plus 13. Oh man, I hit the wrong button. That's what I don't like about phone calculators. I always hit something incorrectly. So I got to type that one over again. 7.2. They're a little bit too touchy for my taste. And I never learned how to do the thumb thing. If you kids are good at that, you go right ahead and do it that way. This is how, I'm going old school. This is why accountants use hard button calculators. It's a little more tactile. 7.265625 plus 13.125 plus 17. Oh no, battery's dying. That's my signal that I've gone on too long. $17.671875 plus 21 plus 23.20325 plus 24.375 plus 24.609,375. So I've got 131.25. So my area is approximately 0.25 times 131.25. Or you could just divide by 4, same thing. And you're going to get 32.81. I'm going to round to 2 decimals after all of that work. And that's it. That's the final answer. That's the decimal. Doing the whole thing with decimals. So the last couple, I showed you both ways. I'll leave it to you. You want to do them all with decimals? That's fine. You want to do them all with fractions? That's also fine. I personally like a balance, you know, do some problems with decimals, some problems with fractions. Sometimes I regret the choice I made. Like this one might have actually been a little easier with fractions. The 0.25 would have been 1/4. All of these decimals, you know, would have an equivalent fractional form. And who knows, it might have been easier. You never know. Until you've done it both ways, and then you decide, you know, which way was more useful. This is quite a section. I've got midpoint method coming next time. So instead of taking the point on the left or taking the point on the right, maybe take a point right down the middle. Perhaps a random point. You know, doesn't have to be left or right or middle. And then some more notation coming in the next part of this video. But I've already gone on too long for one lesson. So I'm Dr. Jordan. Until we meet again, I'll see you on the internet.